Welcome once again to this course on convex optimization. Yesterday we ended our course talking about projections and normals, because we had symbolized the subdifferential of the indicator function as in the normal cone to a set at that point. So, it is very important to know what is actually that normal, a normal cone. Now, it is where we had finished in the last lecture that for every point outside there is a to a closed convex set C, there is a point on the set, basically on the boundary of C, such that the distance x minus x bar, the norm of that provides the minimum distance, or that gives you the distance of x from the set C. Now, let us look at certain interesting properties the normals follow. Again, take this convex set, take this point here, which is say a projection point of this x, which is, and this is x bar, and or like maybe I will call it, I will just call this as y x, because y is what we were denoting as points in C, and y x is the projection of the point x. So, we will write this as the projection of on C, of x on C. And now, you take any other point, say y in C, and join it with y x, then this angle, if you observe, is an obtuse angle. So, which means that the inner product of this and this vector is less than equal to 0, and this is true for any y you take. Take any other y, say y dash, you will have the same thing. But interestingly, this is a necessary and sufficient condition for the point y x to be the projection of x on C. So, let me write down a very important result. The point y x element of C is the projection of x on C if and only if x minus y x inner product y minus y x is less than 0. So, it is a if and only if condition. So, it is instructive to go through the proof of this. So, we will do the proof. So, how do we go about doing the proof of this fact? The proof is as follows, that you have taken, in our case, our f y is of course, this f is dependent on the x naturally. Now, take any y in C and consider y x plus lambda times y minus y x, where lambda is a number between 0 and 1. So, because these y x and y both are in C, we have y x plus lambda y minus y x as an element in C, since C is a convex set. Now, what do I know? Suppose I know that y x is the projection. So, we are starting with the fact that y x is a projection. So, here we have started with the fact that y x is a projection. So, if y x is the projection, so it would imply that f of y x must be the minimum, y x is a minimizer. The projection points are obviously minimizer of this function. So, minimum, so because this is an element in C, so it will obviously sorry. Now, writing down this in the functional form, this would give me half of norm y x minus x whole square less than norm of y x minus x plus lambda y minus y x. So, this if I write down, so this will become, if I open up the norm y x minus, this was half. So, half norm y x minus x whole square plus half into 2 into y x minus x, lambda outside, and y minus y x plus lambda square times norm y minus y x whole square. Now, this will cancel off. So, you would have 0 greater than equal to lambda times norm y x minus x and y minus y x plus lambda square Now, if I divide, now I can divide because lambda is between 0 and 1, I can divide both sides by lambda and I will obtain this expression. We will obtain 0 is bigger than y x minus x into y minus y x plus lambda times norm y minus y x whole square. Now, as lambda goes to 0, we have, when it is positive and going down to 0, we have this would imply x minus y x, inner product y minus y x is less than equal to 0. Now, since y was arbitrarily, it was just any element in C. So, this is true for all y in C. Now, suppose I have this result, this result is been given to me. So, suppose this is true, the question is y x the projection of x on C, that is the question. So, we are going to prove that yes, it is. So, there is a beautiful result which has this beautiful correspondence. So, okay, what you have is the following: 0 is bigger than x minus y x, y minus y x. So, again you can write this as y minus x plus x minus y x. So, again this would become, if you do the inner product, x minus y x to x minus y x plus x minus y x into y minus x. Now, this is nothing but x minus y x whole square, and by using the Cauchy-Schwarz inequality, this is obviously greater than minus of norm x minus y x. Cauchy-Schwarz. Now, this means that I can now take on this side and cancel off this x minus y x, and so finally, I will get the following inequality. I will get that norm of x minus y x, which is same as norm of y x minus x, is less than equal to norm of y minus x, but y was any arbitrary element in C. So, it is true for all y in C. So, this relation would hold for all y in C, because this is true for all y in C. So, this would immediately mean the following, that y x is the projection, because it solves the projection problem, and that is it. So, if I talk about the normal cone, you now see how does that idea of normal cone comes. Now, this x minus y x, this term, if I write it as v, then I have this expression. Now, this v is called, as we have already seen earlier, so v is called the normal, this x minus x bar, which is v in our case, is called the normal to C at x bar. So, v is called the normal to C at x bar. C at y x, sorry, not x bar, y x. So, as you have observed from the picture that there can be more than on one x to which y x is the projection. So, there can be more than one such v's for which this is true. So, let us take the collection of all such v's in Rn such that, so I take a point x bar. So, I take a point x bar in C and take a collection of all those v in Rn such that this is true. Now, if you look at this set follows the definition of a cone. If you take any v, then lambda v is also an element of this set. So, this set is called the normal cone, the cone of normals basically, to the convex set C at the point x bar. A normal cone, as we have seen, is a vehicle for representing optimality conditions, and you see how the subdifferential notion of the indicator function is linked directly to this geometrical thing. So, it also shows that at a certain level the subdifferential is also a very geometric thing, and also brings in the fact itself depends so much on the geometry of the space, and as a result of which a lot of enriching happens and a lot of interesting things get revealed, because this interplay between analysis and geometry. Now, once you have this, the question is, of course, if I put 0, 0 would satisfy this equation, and so 0 must be in the normal cone, okay, that is fine. But suppose I have a set like this, this is my set, this is my set C, and okay, here you draw the normal cone, it is like this, this is my x bar. But you might ask me, then where is your 0? 0 is here, but x bar is not 0. Actually, this is nothing but a translation of the usual original normal cone. To draw the normal cone, taking 0 as the base point or the vertex, you draw lines parallel to this one. So, this is actually your normal cone to C at x bar, and this is nothing but a translate of this to the point x bar, that is x bar plus NC x bar. So, this tells you that okay, if I take the origin of this to x bar, then this is what will happen, then the normal cone is exactly this, if the origin is now x bar. Okay. Now, once I know about this, the question would, I would have some very interesting calculus about normal cone, which I will show you, which will help us to do a lot of interesting things, and which would help us to do write down certain optimality conditions. Let us go back and let us slightly complicate the minimization problem, the convex minimization problem that we had studied. So, suppose I want to take minimize the function f x subject to m inequality constraints and remaining is affine constraints h I x, h j x equal to 0. So, I can now make this compact, this is convex and differentiable, this is, these functions are convex and differentiable, and affine functions are anyway, these functions are affine. So, these are convex and differentiable. This problem can be equivalently set up like this: minimize f x subject to an I where A is a k cross n matrix. Now, how do I write this? Because each h I h j x can be written as a j x plus b j. Now, there are k such constraints. So, linear plus some translation, that is what the meaning of an affine functions. Now, once you have this, because otherwise you know the full feasible set won't be a convex set. So, my C here is now described like this. So, if you look at this, if I take A j to be a row of a matrix, so A1 A2 dot 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 A k, so they form a k cross n matrix, which is A here, and B1 B2 B k is the number of these constants. So, they would form a vector B. Now, this C here this is how I can write my C. So, if I want to write the optimality condition, it becomes 0 is an element of grad of f x, suppose x bar is the minimum. So, x bar is a minimizer if and only if this holds. Now, you see computing the whole question now lies as how to compute. We have studied the Karush-Kuntakar conditions just in the last lecture, I guess. This is what we had studied, the Karush-Kuntakar conditions. Now, how do I reach the Karush-Kuntakar condition? Here we have come to the Karush-Kuntakar condition by applying the max function, the calculus rule. Now, suppose I am not having in hand this calculus rule, what am I supposed to do? Now, you observe that this set C is quite a complicated set. It is not such an easy set that you can compute the normal cone. How do I compute the normal cone for this set? Do I need certain conditions to compute the normal cone? But at the end, first let me write this C as two simpler sets. So, let me write C as C1 intersection C2, where both of them are convex set, where C1 only deals with the inequality constraint, and C2 deals with the equality constraint or affine constraint. So, the normal cone to C at x bar is now written as normal cone to C1 intersection C2. So, how can you compute the normal cone? Basically, you have two convex sets and you have this is the intersection zone, and take any point here or say here, and you are supposed to compute the normal cone. You see here again this relation between the subdifferential of the indicator function and the normal cone, that the normal cone is nothing but the subdifferential of the indicator function, would become very important. The indicator function of C1 intersection C2 is same as writing the indicator function of C1x plus indicator function of C2 at x. Because you see, if there is an x which is both in C1 and C2, then this would be both would be 0 and hence this will be 0. If so, the equality holds. Suppose x is in C1 but not in C2, then x is not in C1 intersection C2. So, this would be infinity. So, x is in C1, so this would be 0, but this would be infinity, but 0 plus infinity is infinity by our law. So, this inequality holds. Now, this means the subdifferential so, again these are proper lower semi-continuous convex functions, and of course, I have not defined much about lower semi-continuous convex functions, we just will do it very soon in much more detail. Let me just tell you, okay, the sum rule that we have learned there is applicable. Assume that C1 and C2 is having interiors. So, an interior of C1 intersection interior of C2 is not empty, like this one. So, then you can apply the sum rule, the calculus rule, to write and this is nothing but and what is this? This is nothing but the normal cone to. See how the calculus rule for subdifferential gives you a calculus rules for the normal cone, and that is the beauty, the link between the geometry and the analysis. And let me tell you what I mean by lower semi-continuous function, otherwise every time I use a term you might be a bit worried. Is lower semi-continuous if its epigraph, if and only if, so I write double F, if and only if its epigraph is closed. So, look at the function DC for a convex set. Take an example, take C to be 0 1. So, that function would look like this. That function would become 0 between 0 and 1, and then it will be plus infinity otherwise. So, this is the epigraph, and of course, the epigraph is closed. The epigraph is of course closed, and hence del C is a lower semi-continuous function. So, for any closed set C, this is a lower semi-continuous function. Of course, the set has to be closed. If the set is open, then it will not be true. Now, I have given a very geometric definition of lower semi-continuity, but there is also a more mathematical definition, but looking at the audience, I would not like to put it. But for those who are mathematically oriented, just I want to remind them, this simply means that so if it is lower semi-continuous at x, this is what it means. So, this is a notion of Liminf, which might not be clear to many students and which we do not want to deal with. So, for us the geometrical definition is the most easy definition, because all the examples that we will do, we can hand it with this, and you need not get so much worked up with this lower semi-continuity business, because at the end we will be dealing with continuous functions from Rn to R which are continuous, and of course, they are all nice and helpful things which you understand pretty well. Now, my problem becomes, optimality condition for my problem becomes, so in order to get the Kuhn-Tucker conditions or Karush-Kuhn-Tucker conditions, I have to compute this and compute this. So, what comes out is that the Lagrangian multipliers or the Kuhn-Tucker multipliers, those lambda y, lambda i's, they are not just ordinary multipliers or auxiliary variables that you use to convert a problem from constant form to unconstant form, but they are deeply linked with the geometry of the space that you are working in, the feasible set. So, our task could be to compute this as well as task could be to compute this. So, let me first today do the easier one, that is, let me compute n C2x, where C2 is set of all x such that Ax equal to b. What we will show is that n C2x bar is nothing but the image of A transpose. A transpose viewed as a linear mapping, every matrix is a linear map and vice versa. And in order to do so, how would I go about doing so? So, what is image of A transpose? If I have the image of A transpose here, then it is a set of all z such that z is equal to A transpose lambda for lambda element of R k. So, first let me take a z, consider z element of image of A transpose. Then z is equal to A transpose lambda. So, let me compute this quantity. So, if this is my V, so the normal if this must be in the normal cone, let me see whether it is in the normal cone. Then take any x in C and take the x bar. compute this. This must be less than equal to 0 for this has to, if this has to be in the normal cone. So, this would imply lambda times A of but this means A x minus A x bar. But if these both are in C, then both are equal to B. So, since now this would imply that A transpose lambda is element of the normal cone to C 2 at x bar. So, now I have to look for the reverse one. So, my next question is normal cone to C 2 at x bar subset of image of A transpose? Let us try out. Okay. Suppose I am having this problem, how will I try out this problem? That is the question. The way to try out this problem is as follows. You can, it is very difficult to take a V and prove that it is an image of A transpose, because V in C 2 is okay. C 2 is a point where A x is equal to B and nothing you know about C 2, the structure is not very clear. So, how do you go about it? You go about it in this following pattern. Let me take a V in NC 2 x bar and so I am assuming on the contrary, I am assuming something which is contrary to what I want to prove. Take V here and let V not be element of image of A transpose. The image of A transpose is a closed set and we had already spoken about the separation theorems in the very beginning, which says that okay, if V is not in the image of A transpose, since image of A transpose is a closed convex set, then what should I do? We should do the following. So, I can now apply the separation theorem. So, there exists a P not equal to 0, P element of Rn such that P of Z, the supremum over, okay, I will just do it much, because you are talking about strict separation, because we can talk about strict separation. By strict separation, let me write down the principle, because you might just forget it why we are doing it. By strict separation, by the strict separation there is a P in Rn and alpha in R such that this is less than equal to alpha strictly less than P of V. Now, what does the Z for, and this is true for all Z element of image of A transpose. Now, what I want to show from here is that P is element of kernel of A. That is exactly what I want to show. So, now what we would do is the following, is that here let us, what is Z? Z is an element of the form A transpose lambda for all lambda in R k. So, this would be satisfied for all lambda in R k. Now, how do I claim that AP is in kernel of A? I claim AP is equal to 0. If I claim such a fact, then I need to prove it. You see, suppose AP is not equal to 0. So, then there exists a say jth component such that the jth component of APJ is either greater than 0 or less than 0. So, let me take this to be strictly greater than 0. Does not matter, this can be done without loss of generality, you can do negative also, does not matter. So, this is true for all lambda. So, since it is true for all lambda in RK, take lambda in RK such that lambda jth component of lambda is positive and lambda any other component lambda ith component of lambda lambda I is equal to 0 if I is not equal to j. Then you can make this lambda as big as you like, as big as you like, as big as you like. So, this will be positive number which can grow in such a way that it will blow up and it will cross this value of alpha, cross this value of PV and break the separation inequality. So, now what we said is that we can blow up AP lambda. Since I can blow up AP lambda, so that would break the inequality, that would break this inequality. Let us write star break. So, I cannot do that, I cannot break that. So, there is a contradiction and so AP is equal to 0 and thus P is element of kernel of A. Now, I give you a homework to prove that P is actually element of C minus x bar, that is P can be expressed as some x element of C minus x bar for some x in C. In fact, you can show that kernel of A is C minus x bar and this is independent of the x bar. This is an easy exercise, just do it as homework. So, what I now get is that once I have this is AP is equal to 0, I will get P of V strictly greater than 0. Since AP is equal to 0, we have PV strictly greater than 0, but P is equal to x minus x bar. Therefore, V of x minus x bar is strictly greater than 0, but since V is element of, so here it will be C2, sorry, not C, C2, C2x, C2. So, V is element of NC2 x bar and that would imply V x minus x bar is less than equal to 0 and then thus a contradiction. So, there our initial claim that there is a V in NC2 x bar and V is not in the image of A transpose is wrong, and hence, so we conclude that NC2 x bar is also a subset of image of A transpose. So, we have proved both ways, this is subset of this and this is a subset of this, and so we will have NC2 of x bar is equal to image of A transpose. So, with this we end the talk here, and in the next lecture we would like to compute this one, which would be very interesting, and you see the role of the Slater's condition. Thank you very much.